Morning folks, today we're going to talk about exponential functions. We're going to look at some of the parts of the function and how to graph them, and then we're also going to look at transformations. So let's go ahead and get started. Like any function that's written in function notation, if we have f of x, that's going to be the output, or y. It also could be the ending amount, and so when we're talking about word problems, very often this is what we're going to end up with. And then the next part is going to be their y-intercept, that's where x equals 0, or the initial amount. A lot of times in word problems, when we have an initial amount or some amount we start with, that's the number that's going to go there. And keep in mind, when we're talking about exponential functions, what we're doing is we're multiplying by the same number over and over and over again. That number is going to be inside these parentheses here, and if it's a bigger than 1, well, if I multiply anything by a number bigger than 1, it's going to grow. We call that a growth exponential function. And then if it's multiplied by a number between 0 and 1, for example, 1/2 or 1/4, that's going to make it smaller and smaller. So we call that decay. I'm pretty sure you've heard those terms before. This x up here, that's the number of times we multiply b over and over and over again. If it's an interest problem, then a lot of times this is going to be years, and if it's a word problem, if it's going to be the number of times we multiply b over and over and over again. So let's take a look at this function right here and see if we can identify the key parts. First, the output, that's going to be f of x. The multiplier is going to be 1/2, and so that means this is going to be a decay function because the multiplier is between 0 and 1. Our initial amount is going to be in front of the multiplier, so that's going to be 4. And keep in mind, if I were to write that as a y-intercept, it would be 0, 4. And when I graph it, it's going to look something like this. So like any function, if I were to plug in different values for x, for example, in this case, if I were to put in a 0 for x, well, anything to the 0 power is going to be equal to 1. And so then my point would be 0, 4, which you can see here we've got graphed. And then if I were to put a 1 in there, so if I made this a 1, well, 1/2 to the first power, and keep in mind, following order of operations, I've got to raise to a power before I multiply. So 1/2 to the first power is 1/2, and then 4 times 1/2 is going to be 2. So if I put it in a 1, a 2 is going to come out. So like any function, that's where these points are going to come from. And then you'll notice that as the x's get bigger, the y's get smaller, and that's why we call it decay. And in fact, as the x's get bigger, it gets smaller faster. That's another characteristic of an exponential function. Now, another key feature for an exponential graph is this horizontal asymptote. If I take 4 times 1/2 and raise it to a number, well, the thing is, there is literally no number that I can put up here in this x that's going to cause this to equal 0. So this graph is never ever going to touch 0. In fact, there's no way it's ever going to be negative, so it's not going to go below 0. So here we got another one. We've got f of x is equal to 1/2 times 3 to the x power. All right, if you look at the multiplier, you see the multiplier is 3, so clearly this is big growth. The number in front of the multiplier is 1/2, so that's going to be our initial amount. And then our y-intercept, well, that's going to be 0, 1/2, or 0.5. If I graph this one, you'll notice as the x's get bigger, the y's get bigger. That's why we call it growth. And you'll also notice that as the x's get bigger, the graph grows faster and more steep. So that's another characteristic of an exponential function. As it gets bigger, then whatever it's doing, growing or decaying, it's going to happen faster. And then we've got our points here. And keep in mind, it's also got a horizontal asymptote of y equals 0. So I guess the takeaway is going to be that if you don't have a number added to the end, you just have initial amount and then a multiplier to some x, then it's always going to have a horizontal asymptote of y equals 0. Now, one of the things we're going to have to be able to do is identify whether a table is got an exponential function. So what I want to do is look at a couple other ones first. if you wanted to identify a linear function, all you would do is take as long as the x's are going up by a constant amount, and you know they are in this case, they're going up by 1s, then all I'm going to do is subtract 8 minus 5 is 3, and 5 minus 2 is 3, and 2 minus negative 1, well, that's the same thing as 2 plus 1, that's 3. And negative 1 minus 4, or negative 1 minus negative 4 is the same thing as negative 1 plus 4, that's 3. What happens is that my y's are actually increasing by 3. And so every time x goes up by 1, my y goes up by 3. We call this a constant rate of change because it's just adding the same number over and over again every time. And that's the characteristic of a linear function. So if you take a look at as the y's are changing, if all that's happening is you're adding the same number over and over again, then you're looking at a linear function. Now, if I want to do the same thing for a quadratic, well, when I take those y's and subtract them, what I'm going to find is I'm going to get different numbers every time. However, when I take the numbers that I got and I subtract those from the one before them, I'm going to get the same number every time. So that's a characteristic of a quadratic function. Now, an exponential function is similar to a linear function. However, in a linear function, we add the same number every time. In an exponential function, we multiply by the same number every time. So again, a lot of times it's easier to start with the biggest one and then go backwards by dividing. 9 divided by 3 is 3, and 3 divided by 3, or 3 divided by 1 is 3, and 1 divided by 1/3 is 3, and 1/3 divided by 1/9 is 3. And again, if I reverse it and go forwards, 1/9 times 3 is 1/3, and 1/3 times 3 is 1, and 1 times 3 is 3, and 3 times 3 is 9. You see how I'm multiplying by the same number over and over again. So is this exponential? Yeah, absolutely it is. And what's our multiplier? Well, clearly we're multiplying by 3 over and over again, so it's 3. Now, is it growth or decay? Well, our multiplier is bigger than 1, so yeah, it's going to be growth. And what's our y-intercept? Well, you'll notice at the table, the x is equal to 0, y is equal to 1, so that's going to be our y-intercept. And if I use this function that we had before, y equals a times b to the x, I can write a function because, see, now I know the multiplier, that's going to be a 3. And so that would be y equals, and then the y-intercept, or the initial amount, is going to be a 1. So I could write it like this, and I've got my function. But typically what's going to happen is I'm not going to put the 1 in front because, you know, that's how we roll with math. We just don't multiply by 1. We don't show it anyway. So that would be an easy way. If I know the multiplier and I know the y-intercept, then I can usually write a function, an exponential function. So let's take a look at another one. We've got this exponential function, and if I were trying to figure out what we multiply by every time, well, it may be kind of difficult to figure out. And so, like I said, if you have trouble, just take the biggest one and then divide by the one before it. If you use your calculator, what you're going to find is that 4 divided by 16 is 1/4. So if you think about it, if I take 16 and divide by 4, I get 4. Well, that's the same thing as multiplying by 1/4. And 4 divided by 4 is going to give me 1. And so is 4 times 1/4. And clearly 1 times 1/4 is going to give me 1/4. And 1/4 times 1/4 is going to give me 1/16. So you'll notice I'm multiplying by 1/4 over and over again. That makes this an exponential function, and it certainly makes our multiplier 1/4. And because our multiplier is between 0 and 1, it's going to be decay. And our y-intercept, once again, is a 1. So if I wanted to write a function, all I would do is write y equals 1 times 1/4 to the x power, and that would be it. All right, now take a look at this graph here. First, is it decay or growth? Well, you can see as the x's are getting bigger, then the y's are getting bigger, so that's going to be growth. If I were to take some of these points here, let's see, I've got, this looks like it's a point. And this looks like it's a point. So you'll notice that as x's go up by 1, the y's go from 2 to 4. So it seems like we're multiplying by 2 every time. We're going to say our multiplier is 2. Our y-intercept is going to be 0, 4. Our horizontal asymptote is going to be y equals 0. And if I wanted to write a function for this, then we're going to say it's f of x is equal to 4 times 2 to the x power. All right, let's try this one. First, is it decay or growth? Well, it's going down. The y's are getting smaller as the x's are getting bigger, so this means it's going to be decay. If I take a look at this one, let's see, once again, you'll notice that I've got a point here, and then if I go to this point here that's 1 away, well, so the x's changed by 1, and here I went from a 3 to a 1, so it looks like I'm multiplying by 1/3 every time. So our multiplier is going to be 1/3. Our y-intercept is going to be 0, 1. A horizontal asymptote, it looks like it's y equals 0 again. So if I wanted to write a function for this, all I got to do is y equals 1/3 to the x power, because the y-intercept was 1. All right, so how about this one here? We've got decay or growth. Well, once again, you can see as the x's are getting bigger, the y's are getting bigger, so this is definitely growth. And if you take a look at our points here, well, here we've got 0, 1. There's a point. And then when I go 1 away, it becomes 1, 3. So, and if I go 1 away again, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So as my x's go up by 1, you'll notice the y's get multiplied by 3. So that gives me a multiplier of 3. Our y-intercept, well, if you look at the y-axis, we cross it at 0, 1. Our horizontal asymptote is still 0, y equals 0. If I wanted to write this function, all I got to do is write y equals 1 times 3 to the x power, and I got it. All right, let's keep going. All right, how about this one then? Is it decay or growth? Well, once again, as the x's get bigger, the y's get smaller. So this is definitely going to be decay. And again, if I take a look at this point right here, it seems pretty clear that that is going to be 0, 3. And then this point right here is 1 away. And once again, I got a 1. So I go from 3 to 1. I must be multiplying by 1/3. That makes sense because it's a decay. Our y-intercept is 0, 3. Our horizontal asymptote is going to be y equals 0. And I'm once again going to get a function of y equals, our initial amount is y-intercept is 3. So y equals 3 times 1/3 to the x power. And then I want you to refresh your memory about transformations. You know, if we add a number at the end of a function, it's going to cause the whole graph to shift up. And if I take away a number from the end of the function, it's going to cause the whole graph to shift down. And if I add a number to just the x's, it's going to make it go to the left. And if I subtract a number from the x's, it's going to move to the right. And if I multiply the entire function by -1, it's going to reflect over the x-axis. If I multiply just the x's by -1, it's going to reflect over the y-axis. And if I multiply the entire function by a number bigger than 1, then it's going to cause a stretch. And if I multiply the whole thing by a number between 0 and 1, it's going to cause a compression. It's going to grow slower. Here are some examples with exponential functions. If I have y equals 2 to the x and I add 3, it's going to cause the entire graph to go up by 3. If I have y to 2 to the x and I've taken away 6 at the end, it's going to cause the whole graph to shift down by 6. Here you'll notice that I'm just taking away a 2 from the x's. That's going to cause it to go to the right by 2. Here you'll notice I'm adding a 1 to just the x's. That's going to cause it to go 1 unit to the left. Here I am multiplying the whole thing by 6, so it's going to cause a stretch by 6. Here I multiply the whole thing by 1/2. That's going to cause it to compression, or it's going to grow slower by a factor of 1/2. And we also have these reflections where we multiply by -1. This is going to cause it to reflect over the x-axis. And if I multiply just the x's by -1, it's going to reflect over the y-axis. And so once again, we've got our graph here. First, we'll start off with f of x equals 2 to the x. And then you'll see the one in blue has got a 3 in front of it. That's going to cause it to have a y-intercept of 3. But you see, to get that 3, it's going to have to grow faster. It's going to be a stretch. And then we've got the other function over here, which is y equals 2 to the x. But this time we're going to multiply it in front by 1/3, which is going to cause it to grow slower, causing the y-intercept to go from 0 to 1/3. And then we've got this function here, where it starts off y equals 3 to the x. And you'll notice that what we've done is we've added 2 to the x's in the pink. And so that's going to cause the whole graph to shift to the left. And then the other one on the other side, if I start off with y equals 3 to the x, and instead, if I were to take away 2 from just the x's, that's going to cause the whole graph to shift to the right. And then you'll notice that if I take y equals, or f of x equals 2 to the x, that's the yellow one in the middle. And if I were to add a 3 at the end, it's going to cause the whole graph to shift up by 3. Now keep in mind, the y-intercept used to be 1, and now it's going to be plus 3, so it's going to be a 4. The horizontal asymptote used to be 0, and now it's going to be plus 3, or y equals 3. And if I go the other direction, so in this case, I take away 3, that's going to cause the whole graph to shift down by 3. So once again, the y-intercept is now going to be 1 minus 3, or -2, and the horizontal asymptote is going to be y equals -3. So keep in mind, those numbers at the end, they're going to cause changes in the horizontal asymptote and the y-intercepts. So we got an exponential function, and it's got an output and an input, and we've got an initial amount and a multiplier. So that's all we're going to do for today. Thanks for watching. I hope that helped.